In this video, we begin Unit 15, the sources of the magnetic field. So first of all, we will focus on the magnetic field generated by a point charge that is moving, and then we will look at the magnetic field created by currents, which are many point charges moving. And at the end, we will look at Ampere's law, which is the equivalent to Gauss's law for the electric field. So to begin, our description of the magnetic field generated by a point charge, we can imagine a point charge. Let's think it's positive, and it's moving upwards with a velocity v, and we want to know what is the magnetic field generated at this point P. So I'm going to call R to the vector that gives you the distance between the point charge and point P. Okay, so its modulus is going to be given by R, and R hat is going to be just the unit vector in the direction of this vector. Okay, so the magnetic field provided at that point P is going to be given by mu0 divided by 4 pi, which is a constant, times the charge times the cross product between the velocity and the unit vector in the direction of r, divided by the square of the distance. Okay, so this is the magnetic field provided by a point charge. Just to let's discuss in this picture what would be the direction of this magnetic field at this point P. So to get this, we need to discuss what is going to be the direction of the cross product between the velocity and the unity vector in the direction of r. So as you know, if the velocity and the unit vector are not parallel, they form a plane. In this case, the plane they form is the plane of the screen. Okay, because they both belong to the screen. So their cross product has to be a vector that is perpendicular to the screen. Now that we know this, the only thing remaining is to know if it's going to go into the screen or out of the screen. And to deduce this, we can use our right hand. And to use it, we will get the first vector, which is the velocity, in the direction of our index. And the second vector is going to be the vector of the unity vector r hat. So and that we put in our middle finger, and then we are left with our thumb pointing into the screen. So that means that the magnetic field at this point is perpendicular to the screen and going into the screen. So that we represent with an X. Okay, that's what it means. If the charge were positive, everything is the same, except that at the end we have to change the sign. So that would be a vector that is again perpendicular to the screen but going out of the screen. So we would represent it with a point. Okay, here I'm supposing that the charge is positive, so I leave it like this. Okay, so there are several things I wanted to highlight here. One of them is this constant. This is a constant called magnetic constant, or permeability of the free space, and it's equal to 4 pi times 10 to the minus 7 Tesla times meter divided by ampere. Okay, it's a constant that measures the magnetic properties of the medium. In this case, we're thinking of the atmosphere, of the vacuum, and then we use the magnetic constant for free space. Okay, so I want to at this point I want to bring back the electric field. If you remember from our deduction of Coulomb's law, the electric field is equal to 1 over 4 pi epsilon sub 0 times the charge times 1 divided by square r, and then this is r hat. So there are several differences and similarities between the electric and the magnetic field. So if we want to highlight similarities between the electric field and the magnetic field, we could say that both are proportional to the charge. So in both cases, the bigger the charge, the bigger the field. Okay, and then we also can highlight that they are both proportional to 1 over square of the distance. So the further away we are from the charge, the weaker the magnetic and the electric field are. There's also these constants that in both there are these constants, okay, and for differences between the electric field and the magnetic field, well, one of the biggest differences is the electric field is parallel to r hat, so it's parallel to the vector that gives you the distance between the point charge and the point that is suffering the electric field, but the magnetic field is parallel to the cross product between the velocity and r hat. This means that the magnetic field is perpendicular to the direction of the vector that gives you the distance between both points. This is a big difference between them. There's another difference that that the electric field does not depend on the velocity of the charge, but the magnetic field depends on the velocity. So it needs a charge moving, because if it doesn't move, if v is 0, then the magnetic field is 0, which is not the case with the electric field, okay? And of course, if the point is parallel to the velocity, then again the magnetic field at that point is 0. Okay, so there are big differences also. There are similarities and differences between both. Okay, so let's use this for a simple example, which is just a point charge moving. Okay, so let's think of a point charge here that is moving in this direction, and we want to know what the magnetic field around it is. So this is the expression, okay, and I want to calculate what the magnetic field is around this charge. Okay, so this is a charge, it has charge Q, okay, and it's moving towards up. So we can start by a point that is, for instance, here, and you can see that this that the direction of the magnetic field, as this is R, the direction of the magnetic field has to be perpendicular to the screen. And if you use your right hand, with the rule of the right hand, you will realize that if the charge is positive, the magnetic field is going into the screen. Okay, so if I choose another point like this one here, I'm going to have the same direction. However, it's going to be further away from the point charge, so it's going to be smaller. Okay, so the bigger the magnetic field is going to be smaller as I go away from the charge. If I get in another just to the left of the point charge, we will have, if I'm at the same distance, and this point here, I'll have the same magnetic field, except that in this case it's going to be okay, so I can represent it with a point. And of course, the further away I go, the weaker the magnetic field. Okay, so if I go in this line here, as this line, the distance and the vector v are both parallel, the magnetic field in this line is 0. Okay, if I go to a point, let's say this one, the vector is going to be, the distance vector is going to be this one. So again, the magnetic field has to be perpendicular to the plane that contains both v and r, which is the screen. And we can discuss again with your right hand. You can deduce that the magnetic field at this point is going to be into the screen. So I'm left with something like this. The further away I go in this direction or in this direction, the smaller the magnetic field. And whenever I go in this other, on the left part, I'm going to have this kind of magnetic field. Okay, there's another way to point this, and it's thinking that this is our charge Q. Okay, and now we're looking at it from above. So the charge is moving, and it's at this point it has a velocity that is going, it's a vector that is perpendicular to the screen, going out of the screen. So you just have to imagine that I cannot plot the vector v because I'm looking directly at it. So I can plot it if you want, that's a point. So we could try to calculate what the magnetic field is at this point. So at this point, the magnetic field has to be we have to calculate the cross product between the velocity that is going out of the screen and vector r, which is this vector here. So if we do this, we put the velocity going out of the screen in our index and the vector r as the middle finger going towards the right, then our thumb gets pointing to this part here, okay? If we do the same with this point, we end up having a vector, a magnetic field that points like this, like this, like this. You can discuss all of these. So whenever I'm at the same distance from this point charge, if I draw a circle of radius r, at all these points, okay, all these points have the same magnetic field, the same magnitude, and the direction is going to be given by the tangent of this circle. So the further away I go, if I trace here another circle with a bigger radius, the magnetic field is going to be much weaker, but the direction is always going to be, in this case, tangent to this circle, okay? So with this ends this first part devoted to the magnetic field of moving point charges. And once you've finished this, you could calculate, you could try to solve problem 1 from the problem set that you have.